Hello everyone, my name is Stu Adler. Welcome back to Introductory Lectures in Thermodynamics. During previous episodes, we developed the idea that a system containing one or more aggregate arrangements of molecules, or phases, can be uniquely and adequately described using a relatively small number of continuum state properties at equilibrium. However, before we leap off into theories for how and why these various properties are related to each other in different systems, I think it's helpful to first discuss in general terms our expectations for the type and number of such properties. As you can imagine, the more phases and different types of molecules we have in our system, the more variables we'll need. This can quickly lead to a proliferation of variables and relationships we need to consider. How do we ensure we're focused on the right ones and not leaving out important relationships or overcomplicating our problem? Hence today's episode, Degrees of Freedom in Equilibrium Systems. Let's start with another cartoon. A math teacher's at the board showing his class how to simplify an equation. After he's done, a student asks why not find the person who wrote the equation and ask them not to complicate it in the first place. In the context of chemical engineering, this turns out to be an insightful comment. Many of you have taken Chemi 310, have probably experienced trying to work out the mass balances on some complicated flow sheet involving recycles and half a dozen or more equations and variables. After pages of algebra, you suddenly realize you're completely lost track of all the knowns and unknowns of the problem and have spent the last hour just chasing your own tail. We've all been there at one point or another. Some of you might recall that one way to avoid this trap is to do something called a degree of freedom analysis to figure out ahead of time how many relationships you need to solve a particular problem. Well, it turns out that a very similar situation arises in thermodynamics when we're trying to describe the equilibrium state of a system using macroscopic state variables. We can often save ourselves a lot of grief by thinking in advance about how many state properties and relationships we need to consider. This often allows us to focus more precisely on the properties and relationships that really matter. To begin, consider a system of molecules that only contains one molecular species, also known as a component. Let's say that under the conditions we're interested, these molecules adopt a single homogeneous aggregate arrangement, or phase, at equilibrium. If so, how many state properties do we need to specify or measure to uniquely and adequately describe the system? One straightforward way to approach this question is to consider an isolated system of fixed volume V containing n moles of molecules having a total energy U. Since the system is isolated, N and U cannot change due to conservation of mass and energy. V also cannot change for an isolated system. Another way to say this is that N, V, and U are invariants of an isolated system. Since we've already assumed equilibrium as a single phase, the average aggregate arrangement adopted by the molecules will be unique to these values of N, V, and U. Since any other state properties we can think of, like temperature or pressure, will depend on this equilibrium arrangement, they will also be functions of N, V, and U. Assuming we know these relationships, we can always invert them to re-express V and U as functions of these other variables, for example, N, P, and T. But counting unknowns, we would still need to specify three independent quantities to define both the state and size of the system. So it seems we have our answer. However, you might notice that N, V, and U are all extensive. We can always divide two of them by the third to get two intensive properties, relegating the third variable as a specification of the size of the system. In most situations in thermodynamics, when we consider thermodynamic state, we focus on the intensive properties of the system, not its size, which we usually handle separately or divide out of the problem. This means that we really only need to define two intensive variables to define the intensive thermodynamic state of our system. Another, perhaps more intuitive way to arrive at the same conclusion is to imagine a balloon containing our molecules, surrounded by a gas at temperature T and pressure P. Let's assume that the molecules cannot pass in or out, and that the elasticity of the balloon wall does not contribute significantly to pressure. In order to satisfy the constraints of thermal and mechanical equilibrium, we expect heat and work to pass until the temperature and pressure inside the balloon match the gas outside. If we again assume a unique single-phase arrangement of the molecules at this point, we have defined two intensive variables, T and P, to specify the state of the system. These conclusions are codified in what the author of our book, Milo Koretsky, calls the State Postulate, paraphrased here as follows. For a system containing a single unreactive molecular species, which exists as a single phase at equilibrium, we must specify the value of two independent phase-intensive state properties to uniquely and adequately define the intensive thermodynamic state of the system. This postulate has two important implications. One is that we need to know or control two intensive state properties to know or prescribe the state of the system. The other is that once we specify these two properties, we no longer have independent control over any other intensive properties. At equilibrium, the molecules will adopt a configuration in response to imposing the first two intensive properties, and this configuration determines all the others. One way that workers describe this postulate mathematically is to say that a single-phase system with one component has 2 degrees of freedom, where F represents the number of independent phase-intensive state variables at equilibrium. This statement does not tell us which variables are independent. It only tells us that when we specify 2 variables as independent, all the others appearing in thermodynamic relationships must become dependent variables. In order to better conceptualize what it means to have 2 degrees of freedom, let's explore the thermodynamic properties of a familiar fluid, air. Technically, air is a mixture of O2, N2, and other molecular species. We'll get back shortly to what happens to degrees of freedom in a mixture. But for the moment, let's idealize air as a single-phase gas with one molecular species. Shown here is a transparent glass piston cylinder assembly containing a mass of air sealed inside. The assembly is equipped with a heater and a thermocouple so we can measure and control the temperature, currently about 58 degrees C in this image. It also is equipped with a pressure transducer so we can measure pressure, currently about 14.6 psia. The air inside the assembly constitutes a closed system, since molecules of air cannot get in or out, but we can transfer heat to or from the gas by thermal contact with the metal base. We can also do work on the gas by expansion and compression of the piston. Using this apparatus, we can explore the equilibrium relationships of temperature, pressure, and volume. According to the state postulate, we must specify 2 independent intensive variables to define the state of the system. If so, which ones have been specified here, and which ones are determined by equilibrium? Well, one thing you might notice is that the temperature inside the cylinder, 58 degrees C, is much higher than the outside air temperature. This is because the metal base is already hot from a previous experiment. This base has an enormous thermal mass compared to the air inside the cylinder, so as long as the heat transfer to or from the air is reasonably fast, we expect the air to stay fairly close to this value. Thus, temperature appears to be one of the properties being imposed on the system. You might also notice that no one is controlling the position of the piston at the moment, so it's free to move. It doesn't weigh much and is lubricated with vacuum grease, so we expect it to move up or down until the pressure forces on the top and bottom of the piston are balanced. This expectation is consistent with the current pressure, 14.6 psia, which is close to atmospheric pressure. Thus, pressure appears to be a second property being imposed on the system. According to the state postulate, all other intensive variables we can think of are determined by equilibrium at this temperature and pressure. Consider molar volume, for example. Since the system is closed, the number of moles is constant. However, the total volume is free to change by movement of the piston. The fact that the piston is no longer moving implies that the molecules have spread out and occupied a total volume that ensures mechanical equilibrium at 1 atmosphere. Thus, molar volume is not imposed by us or the apparatus. It's a consequence of equilibrium inside the system. One way to express this idea mathematically is by saying that molar volume is a function of temperature and pressure. At such low pressures, we might expect air to obey the ideal gas law. Taking T and P as the independent variables, we can rearrange it to make the volume dependent. This model predicts the air will expand if we lower the pressure. For example, if we moved our setup to the top of Mount Rainier, where the atmospheric pressure is only 0.6 of an atmosphere, we would expect the gas inside the cylinder to expand, sliding the piston upward until the pressure inside the cylinder also became 0.6 atmospheres. This change in volume is the spontaneous response of the air molecules to an imposed change in pressure at fixed temperature. Changing altitude sounds like an impractical experiment, so as an alternative, let's instead grab hold of the piston and force the volume to change. Since the number of moles is fixed, this corresponds directly to a change in molar volume. If we do this, molar volume and temperature become independent state variables being imposed by our apparatus. But what happens to pressure? Well, by putting our own external force on the piston to hold it in a particular position, the pressure in the system is no longer required to be in equilibrium with the surrounding atmosphere and becomes free to change in response to the imposed volume. As you can see, as we decrease the molar volume, the pressure goes up. Likewise, if we increase the volume, the pressure goes down. We no longer control the pressure. Its value is now a consequence of equilibrium inside the system at a given temperature and volume. Returning to the ideal gas law, this situation corresponds mathematically to rearranging the equation so that pressure is the dependent variable and volume and temperature are the independent variables. However, even though the variables we are now specifying have changed, the number of variables we must specify has not. Thinking mathematically again, the ideal gas law has three variables in it: pressure, volume, and temperature. If we specify only one variable, we don't have enough information to solve for the other two. If we try to specify all three variables at the same time, the problem is overdetermined since the values we chose may not agree with the ideal gas law. We must specify exactly two and solve for the third. One way to visualize this is to consider a three-dimensional or contour plot of the PVT properties of a substance, also known as the PVT surface for that substance. For a gas that obeys the ideal gas law, that surface looks like this. The idea here is that the properties of the gas must lie somewhere along the surface at equilibrium, with each point along that surface corresponding to a different, distinct, intensive thermodynamic state. In order to define this state, we must specify two of the three variables. In our experiment here, we were adjusting volume at fixed temperature, which corresponds to movement along the surface like this. The state postulate takes this idea one step further to say that no matter what the PVT relationships our substance obeys, or whatever other intensive properties we consider, the system must always obey this basic constraint. We still must define two intensive variables to define the intensive state of the system, while all others are a consequence of equilibrium. This is what we mean by 2 degrees of freedom. To see this played out a bit more, let's now compare the properties of air with the properties of liquid water contained in the same apparatus. According to the state postulate, we should again see an equilibrium relationship among P, V, and T, with only two being independent. As with the air, the initial state of the system involves a defined temperature, 25 degrees C in this case, and a pressure of about 1 atmosphere, with a total volume determined by equilibrium. Note that the pressure reading is slightly higher than atmospheric. This is caused in part by the mass of the water, which adds a few tenths of a psi hydrostatic pressure. If we now take control of the piston and begin manipulating the volume as an independent variable, you can see that the pressure becomes dependent. As I press down on the piston, reducing volume slightly, the pressure goes up. As I pull up on the piston, increasing volume slightly, the pressure decreases. However, unlike a gas, water is nearly incompressible. Thus, only tiny adjustments in volume that we can hardly see in the video result in large changes in pressure. As we'll discuss in Chem E 326, this behavior can be expressed mathematically in differential form in terms of the isothermal compressibility and thermal expansivity. The isothermal compressibility of water is very small, meaning that very small changes in volume lead to very large changes in pressure, as we saw in this experiment. As shown here, this corresponds to a nearly vertical PVT surface. In our experiment, the changes in pressure we observed correspond to movement up and down along the surface at nearly constant volume. Okay, so the next question is, what happens if we expand our system to include additional phases? What happens to the number of degrees of freedom, and how many phase-intensive variables do we need to define? To gain some insight, let's return to the example of water in a piston cylinder assembly. However, this time, instead of working with just one phase, let's also generate some H2O gas, much like our imaginary astronaut did. As shown here, we can do this simply by forcibly increasing the molar volume of the system until it exceeds the molar volume of liquid. Unlike a gas, which expands to fill the volume we give it at some pressure, water as a condensed phase cannot do this. Instead of the molecules continuously getting further apart, the entire system splits into two phases, a liquid and a gas. One thing you might notice is that pressure, which previously varied strongly with volume for both a liquid and a gas, the pressure here remains approximately fixed at a low but non-zero value of about 1 psia, no matter what the volume of the system is. In terms of our previous analysis of degrees of freedom, we seem to have lost the ability to manipulate pressure as a dependent variable by altering molar volume of the system. Why is this? I think one way to think about it is that when only one phase is present, like a liquid or a gas, the molar volume of the system is phase intensive. That means that when we change the volume, it is felt uniformly everywhere as a change in molecular density. The molecules must get closer or further apart from each other, and this has a direct impact on pressure as a dependent variable. However, when two phases are present, the molar volume of the system is no longer phase intensive. So when we change the volume, this change is accommodated by a shift in the relative amounts of the liquid and gas, while the intensive properties of the gas and liquid individually remain fixed, including pressure. Since pressure is a function of the molecular density in each phase individually, it cannot change. Instead, it gets stuck at a value where the liquid and gas both share the same pressure at equilibrium at the defined temperature. This pressure is called the saturation pressure. Sometimes when people see this for the first time, it seems really odd, since they expect the pressure to go up and down as we compress or uncompress the gas above the water. But it's not air in there, it's steam, and it's not compression or expansion of steam. It's evaporation and condensation from the liquid below it. So what does this mean for the degrees of freedom in the system? As you can see, we're still imposing a temperature. We're also imposing volume, but it's not a phase-intensive volume. Once two phases exist in any amount, we no longer have control over phase-intensive properties of either phase. The pressure and the molar volumes of both phases are determined by equilibrium. Each time we try to compress or expand the phases in the system, the molecules just readjust by evaporating or condensing, returning to the same intensive thermodynamic state in each individual phase. All we can do is adjust the total volume by changing the quality, the fraction of the system mass that is gas versus liquid. This can be summarized mathematically by saying that the degrees of freedom of the system is now reduced to 1, which in this arrangement corresponds to temperature. So what happens if we change the temperature? Repeating this experiment at 99 degrees C, we can see that the saturation pressure is now much higher, close to atmospheric. In fact, we can actually let go of the piston in this case because the pressure inside is about the same as the outside pressure. This aligns with our understanding of the normal boiling point of water, which is 100 degrees C at 1 atmosphere. In fact, we actually see some active boiling happening. However, that's not a feature of equilibrium. This is a limitation of this particular apparatus. What's happening is that the glass walls of the piston cylinder are not really perfectly insulating, so at this elevated temperature, a lot of the heat escapes out the side of the cylinder. We have to replace this thermal energy by heating the base to maintain a constant temperature. This causes the water to continuously boil and recondense on the sides of the cylinder. However, due to mixing, we still get a reasonable approximation of equilibrium. On that note, some of you may have gone camping at high altitude and noticed it takes a lot longer to cook your mac and cheese at high elevation. Here's the same experiment at about 82 degrees C. You can see the pressure is much lower, about 8 psia, which is just over half an atmosphere. This is the boiling point of water at about 16,000 feet. Here's the system again at about 60 degrees C. This takes us down to a saturation pressure of 3 psia, or about 1/5 of an atmosphere. And here it is again at 35 degrees C, where the saturation pressure is only slightly above where it was at 25 degrees. It's still boiling, you can see the bubbles coming up, but it's cool to the touch because it's only 35 degrees. Okay, so let's summarize what we've seen. With only one phase present, water, or we also saw this with air, we can independently adjust the temperature and the molar volume. If so, pressure is determined by equilibrium. This corresponds to 2 degrees of freedom, which in this case are temperature and volume. However, with two phases present, we can only independently vary temperature. Pressure and the molar volume of both phases are determined by equilibrium. Although we can adjust the average molar volume of the system, in this case, volume is not a phase-intensive property of either phase in the system. It's an average system-intensive property representing the relative amounts of the two phases. This corresponds to 1 degree of freedom, which in this case is temperature. Another way to visualize what's happening here is to make a plot of the saturation pressure that we measured versus temperature. After subtracting the hydrostatic contribution of the water, the data looks like this. As you can see, the saturation pressure goes up monotonically with temperature for reasons we'll ultimately explore. You may recall in Chem E 310 using the saturated steam tables. Taking some of the data from these tables and plotting it here, we can see that our relatively primitive measurement agrees fairly well with established literature values. The resulting line we see is called the saturation line or coexistence curve, indicating combinations of pressure and temperature where H2O gas and H2O liquid can coexist at equilibrium. As we'll discuss shortly, this type of plot is also known as a phase diagram because it maps out and allows us to visualize the conditions under which various phases will form at equilibrium. For example, above the coexistence line, the pressure is too high and/or the temperature is too low to have any steam present. This corresponds to the single-phase liquid region, where we have 2 degrees of freedom. These 2 degrees of freedom can be visualized here as the ability to move along the pressure or temperature axis arbitrarily in any direction while still maintaining a single-phase liquid. Likewise, below the coexistence line corresponds to the gas phase only region, where only steam can exist. Here we also have 2 degrees of freedom. However, along the coexistence curve, where we have two phases in equilibrium, we have 1 degree of freedom. This can be visualized as the ability to move one-dimensionally along the coexistence curve. Along this curve, both pressure and temperature can change, but they are changing together in a way determined by equilibrium. Okay, so how do we generalize these observations to other systems, including additional phases, mixtures with more than one molecular species, or chemical reactions? What happens to the number of degrees of freedom? Well, the answer to this question turns out to be amazingly straightforward. Each time we add a component to a phase, we need to add one additional intensive variable, such as a concentration or mole fraction, to define the composition of that phase. Meanwhile, for each reaction or pair of phases, we must add some kind of equilibrium relationship for each species. Although our ultimate goal is to understand these relationships, we don't need to know much about them to count them. If we do, the net result is a statement known as the Gibbs phase rule, which can be expressed mathematically as shown here. In this equation, the degrees of freedom, F, is the number of independent phase-intensive variables that must be specified to define the intensive thermodynamic state of all phases within the system. C is the number of molecular species comprising the system. P is the number of phases present at equilibrium. And R is the number of independent equilibrium reactions. So for example, if we have one component existing as one phase with no reactions, we get 2 degrees of freedom in agreement with the State Postulate. This corresponds to what we saw for air or single-phase water. In contrast, if we have one component in two phases with no reactions, we get 1 degree of freedom in agreement with what we just saw for two-phase H2O in our piston. Gibbs' phase rule is deceptively simple, but it can also be incredibly powerful. It's basically saying that even without knowing anything about the specific interactions governing a group of molecules, we can still make sweeping statements about what kinds of structures can and cannot exist and how many state properties we need to define the thermodynamic state of the system. These considerations are an enormously helpful place to start an equilibrium problem, since it predefines the number of relationships we need to measure, plot, express mathematically, or seek theoretical models for. To help make this a bit more concrete, let's apply Gibbs' phase rule to a few example systems and see what it can tell us about the properties we've specified in each case. The first is 18 grams of pure single-phase H2O at 50 degrees C. Here we have one phase and one component. So according to Gibbs' phase rule, we should have 2 degrees of freedom. We seem to have two state variables defined here, the temperature and the total mass. But the mass of the system, 18 grams, is an extensive property that defines the size of the system. We don't have any other extensive properties to compare it to determine an intensive property. Thus, so far we have only defined one intensive property, the temperature. So Gibbs' phase rule is telling us that we have an underdetermined problem. We would need to define some other intensive property of the H2O to define its state. For example, we could set pressure to 1 atmosphere, in which case we would have hot water. Or we could define pressure to be 0.1 atmosphere, in which case we would have steam. Next, consider a two-phase mixture of pure water and steam at 0.1 atmospheres and 70 degrees C. In this case, we have two phases and one component. So Gibbs' phase rule predicts 1 degree of freedom. But wait, we've already specified two phase-intensive properties. In this case, Gibbs' phase rule is telling us that the problem is overdetermined. The situation we've described is not physically possible. Examining the phase diagram we made earlier, this combination of conditions would lead to a gas at equilibrium. To have two phases at 70 degrees C, the pressure would have to be 0.3 atmospheres. Alternatively, if we specify a pressure of 0.1 atmospheres, the temperature would have to be about 46 degrees. But we cannot have both phases present at 70 C and 0.1 atmospheres. Okay, how about this one? Pure H2O at 70 degrees C and a density of 0.5 grams per centimeter cubed. In this case, we clearly have one component, but how many phases? You might recall that by definition, the density of liquid water at 0 C is 1 grams per centimeter cubed. We don't expect the density of water to be much more than this at 70 degrees C. Yet the density of our system is only half that. This implies that the additional volume must be occupied by steam. So we have two phases. Applying Gibbs' phase rule again, we have 1 degree of freedom. But in this case, we've defined two intensive properties for our system, temperature and density. The resolution to this paradox is that even though the density is intensive, with two phases present, it's a system-intensive property, not a phase-intensive property of either phase. So it does not count as a degree of freedom in Gibbs' phase rule. Temperature is always phase-intensive, so it does count as a degree of freedom. By specifying temperature, we have already defined the thermodynamic state of both phases. The density is irrelevant information because it only affects the relative amount of the water and steam. We could equally have specified a density of 0.9 or 0.1 gram per centimeter cubed, and we'd be talking about exactly the same intensive thermodynamic state. Okay, one more. A gaseous mixture of H2, O2, and H2O at 1200 degrees C and 1 atmosphere in the presence of a platinum catalyst. Due to the high temperature and the presence of the noble metal catalyst, we expect rapid equilibrium of the hydrogen oxidation reaction. So we have a reaction in this case. Counting components and phases, we have a gas containing H2, O2, and H2O. But do we count the platinum? Well, this comes down to an unspoken first step we need to do first. Draw a control volume. If we place the control volume around the gas only, we would have one phase with 3 components, and can ignore the platinum from the standpoint of Gibbs' phase rule. If we do, applying Gibbs' phase rule, we get 3 degrees of freedom. But what if we include the platinum? Then we'd have 4 components. But we'd also have 2 phases, a gas and a solid. Applying Gibbs' phase rule again, we get, again, 3 degrees of freedom. This is telling us that the presence of the catalyst doesn't impact the number of degrees of freedom in our system. We still need to define 3 phase-intensive properties to define the thermodynamic state. We've already defined two of them, temperature and pressure. So what's the third? Well, as we've discussed previously, intensive composition variables like mole fraction of a species in a gas are phase-intensive properties. So for our example, we could define the mole fraction of H2 in our gas. That would bring us up to the correct number of degrees of freedom. Gibbs phase rule is also telling us that we could not specify any additional mole fractions in the gas. This would consume more degrees of freedom than we have, making the problem overdetermined. Just as an example, let's say we tried to force the mixture to have both 10% hydrogen and 10% oxygen by flash heating this mixture to 1200 C in 1 atmosphere. As we've discussed already, this is a highly exothermic reaction, so almost all the H2 is going to react to make more H2O, leaving behind about 5% oxygen and only trace quantities of hydrogen. On the other hand, if we only specify 10% hydrogen in the final equilibrium mixture, then the oxygen concentration can be whatever trace value it needs to be to satisfy equilibrium of the exothermic reaction. What I hope these examples have illustrated is that applying Gibbs phase rule often allows us to focus more precisely on the properties and relationships that really matter. As we'll see next week, it also helps frame our expectations for the structure of thermodynamic data and models. For example, the form and variables we expect to see in phase diagrams or tabulated equilibrium data, or the properties we expect to see in an equation of state. This gives us an enormous leg up in applying these data and models to engineering problems even before we begin to theorize about the origins of these relationships at a molecular level.